All right, good morning for pre-calculus. So today we get to start talking about inverse functions, right? And the idea for an inverse function, okay, is it has to have the following, well, it has to be a function, okay? But the quality you have to have for an inverse function is that you have to have something that passes the horizontal line test, okay? It has to be something called a function must be 1 to 1. Okay, we abbreviate it with a dash. Okay, it's not 1 minus 1, it's 1 stroke 1. Okay, 1 to 1 function. Okay, which means it passes horizontal line test. Right, you guys did vertical line test before. That's if a function, right? There we go. If a function, if you can pass a vertical line through the thing, it's not a function. Okay, not a function. It can have a formula, right? There's a circle. It's got a formula, not a function though. Okay, well, that's the vertical line test. Okay, that's the vertical line test. Is it a function? But in order to see whether or not it is a, right, in order to see whether or not it is a one-to-one function, it's got to pass the horizontal line test. Okay, so a function like y equals x squared, right, technically does not have an inverse because, right, we can pass a horizontal line through this thing, and it doesn't work. All right, so technically this function does not have an inverse. We'll talk about that in a little bit. Okay, but that's how you tell whether or not something can have an inverse. It's like, is it 1 to 1? Yes. Well, then we can have an inverse. If it's not 1 to 1, no inverse. Okay, so does this function look like a 1 to 1 function? Yeah, it does, because it passes the horizontal line test. Okay, so we could say that, and then we're okay. All right. Let's see what else we got here. How many of these are going to ask you? Okay, so yeah, let's talk a little bit, see if the function defines y as a 1-to-1 function of x. Well, y is, I mean, it is right in a case like this, right? It is 1 to 1, okay, but this is not a function, right? It fails the vertical line test, so it doesn't define, because they use the word function here. It does not. We can't do that. They better say it doesn't work. Okay, if they don't, then I don't know what to do. But it's not a function, so we can't go and say that's going to work. All right, so that's what they're testing there. It's got to be a function, and it has to be 1 to 1 in order for you to have an inverse function. Okay, so be careful about that. They will probably do something to mess with you on that one. All right, now if I ask you, like I said, well, how do I do a square? You're all going to tell me, well, you take a square root. You're right, we do. But it's not quite take a square root, right? They have a principal square root and they have a plus or a minus business, right? So if I said to you, here's y equals square root of x, does this thing have a function? Does this thing have an inverse? Like, absolutely it has an inverse. And the inverse is x squared, sort of. The inverse is x squared if, right, our inverse function is y equals x squared, but we have to modify the domain and we have to say x greater than or equal to 0. Okay, that's where the distinction is between y equals x squared not having an inverse, but y equals x squared, x greater than or equal to 0, or x less than or equal to 0. Okay, this would also, right? That would be just fine as an inverse function as well. Okay, so it really depends. Are you talking about the positive or the negative one of these? And that's how we're doing that. Okay, I know it seems like it seems a little nitpicky. I'm like, you're right, it is. But when you get the trig, that's the kind of thing, that's the way you're going to have to think about this, because most trig functions, actually all the trig functions, technically don't have inverses unless you mess with their domains. Okay, and that's how you define an inverse, is you restrict the domain for it. Okay, so that's what we're doing with this one. So technically, and we are going to be technical, x squared plus 1, that is not a one-to-one function. So this function is not one-to-one, right? But we can restrict the domain of this thing in order to get an inverse function out of it. Okay, so let's see. When do they ask us to figure out what an inverse function is? Determine whether or not they are. Okay, beautiful. Okay, so the next thing is, how do you tell if two functions are inverse functions, right? How to tell if two functions are inverses. Okay, well, do you remember the circle function, right? The circle operator, function composition, okay? So if, and remember, this did not go both ways, right? We had G circle F and F circle G. These were not the same, right? These are not the same. But if F circle G of X equals X and G circle F of X equals X, then F and G are inverses. Okay, so that's how we're going to tell. And again, we have to make sure that it works in both directions. You can't just do one and say, okay, well, I checked it one way. I'm like, no. This doesn't commute, so you have to check both ways. All right, so be aware that that's something that might have to happen. So we have a 2x plus 3 and an x minus 3 over 2. Okay, so your book isn't really all that clever about like trying to hide things from you. So generally it will be, but properly, there's f. And g of x is x minus 3 over 2. Okay, so are these inverse functions? Well, let's try it the first way, right? Let's do f of g of x. Okay, and f says we're going to take 2 times some number and then add 3 to it. Okay, that's what f says to do, is take 2 times a number and then add 3 to it. What number would you like to multiply by 2? Well, I'd like to multiply x minus 3 over 2. Okay, so we're just going to put this into this box and then evaluate. So our 2's cancel, right? And we have x minus 3 plus 3, and we end up with x. Well, looking promising. What if we go in the other direction? What's G say to do, right? What's G of f of x? Well, G says you take a number, subtract 3 from it, and then divide the whole thing by 2. Okay, so we're going to take a number, we're going to subtract 3 from it, and then divide the whole thing by 2. Well, what number would you like to subtract 3 from? Well, how about 2x plus 3? So what we're going to have here is 2x plus 3 minus 3 all over 2. Does it make sense that those cancel? Then we have 2x over 2, which is equal to x. Good. So they worked in both directions. F and G are inverses. Okay. Okay, f and g are inverse functions. Great. So when I go back to here, it says the 2 functions are inverses. All right, fantastic. Let's see, how many more of these do they ask? We just did that one. Okay. Now, the interesting thing is, great, we can test whether or not they are inverses. We'll get to this one. This is a good one. But how do you tell how do you figure out how to find one? Okay. So the steps to figure out an inverse function, okay? Rewrite the function as y equals some kind of formula here, okay? So for our first example, right, maybe we'll try to find f's inverse. So 2x plus 3. So we'll say y is equal to 2x plus 3. That's your first step. Second, well, your first step is, should I even bother looking, right? Is it a one-to-one function? But since we know that's a line, we know it's one-to-one. Okay, so is it one-to-one? You write that function down. Then what we're going to do is we're going to swap x, let me not put equals, let me put x2y. Okay, we're going to write x is where the y is, and then y where the x is. So we have x equals 2y plus 3. Right? And then the third thing we're going to do is we're going to solve for y. Okay, if you can. So, right, that's going to be subtract 3 from both sides. So we're going to have x minus 3 is equal to 2y, or 2y is equal to x minus 3. Divide both sides by 2, and we have y is equal to x minus 3 over 2. Now, you weren't surprised here because you knew what was going to happen because of the initial condition here, the initial problem. You knew it was going to be x minus 3 over 2, and we just proved that. Okay, well, we didn't prove it, we just found it. Okay, technically the next step is check it. Okay, and that's how you check. All right, so what if we have one that's a little bit more interesting? We have a 3x cubed minus 4. Okay, so we have our function here is equal to 3x cubed minus 4. Yeah? Yeah. And they want to, oh, we have m of x, not f, whatever. All right. The job is find m inverse. Okay, so what we're going to do is we're going to say y equals 3x cubed minus 4. You know that this is a one-to-one function because you know what a cubic looks like. That has a vertical shift of a 4 down and a stretch of 3. Okay, so if I were to solve for, set this equal to 0 and solve, right, we get the cube root of like 4/3 or something. Actually, we're just going to get negative 4. Okay, and I know what cubics look like, and that's what they look like. So I know this thing passes the horizontal line test. Okay. I don't think your book is mean enough to like ask you to like get in the thick of it and find stuff and then say, oh, we fooled you. It wasn't really a function. I don't like to do that either, by the way. I had a teacher that would do that to us on a regular basis. 5 freaking problems on a test. And one of them was a gotcha question. Okay, so we're going to swap. Okay, so we're going to say this is x is equal to 3y cubed minus 4. All right. And then we're going to solve for y. All right. So add 4 to both sides. We have x plus 4 is equal to 3y cubed. We could also say 3y cubed is equal to x plus 4. Let's divide both sides by 3 here. So we have x cubed is equal to x plus 4 over 3. And then y is equal to the cube root of x plus 4 over 3. All right, and there is our inverse function. Okay, so m inverse, right, is the cube root of x plus 4 over 3. Okay, and I didn't need to restrict the domain, so we're fine. We'll talk about that in the next one. Hopefully they'll give us a good problem. Okay, so this was, they even knew, look at that, the cube root of fraction 2, right? And this was x plus 4 over 3. Is that the right one? Double check here. X plus 4 over 3. Looks good. All right. This is a good one. Okay. So are we given a one-to-one function? Well, we just spent how much time trying to figure out how to graph rational functions, right? So if you have a linear over a linear, right, there's no weird turning back and turning around or anything. Nobody's going to cross an asymptote. but we have horizontal asymptote of 1. Oh, this is not a good problem. And vertical asymptote of 1. Okay. It would have been better if there was a 2 up here. As a matter of fact, you know what? We're not going to do the same problem. We'll do the different problem here slightly, because I want to show you something. 2x minus 3 over x plus 1. Oh, I can't even write it down right. All right, let's go ahead and fix this. I didn't want to change it too much. I just wanted to change one little letter here. One little number, rather. Okay, so we know, right? There's no common factors because there's nothing we can cancel. So common factors, none. Okay, 2, vertical asymptote. Pretty easy on this one, right? X equals -1. Horizontal asymptote. Which version are we in? Well, the degree of the top is the same as the degree of the bottom. So we're going to have the line. These are the lines. Right? So we're going to say y, the line. We'll say the line. Y equals 2 over 1. Okay? So the horizontal asymptote is the line 2 over 1. Okay, so we're not quite working the same problem here anymore, but I want to show you something. Okay. Yeah, oh well, I messed up. We could have worked that problem. It would have been okay, but all right. So now we get to go find our inverse. So step 1, right, was to write down y equals 2x minus 3, x plus 1. Okay. Step 2, swap. So we're going to say x equals 2y minus 3, y plus 1. Okay. By the way, this is my favorite flavor of an inverse function problem. So if you're looking like, what could he possibly want to ask on an exam? This one. So we have to solve this. How do we solve a rational equation? Well, the first thing we do is we make it not a rational equation. So we're going to have x, y plus 1 is equal to 2y minus 3. You see what happened there is I multiplied both sides by y plus 1 to cancel this and to put it over here. Okay. So what are we going to have? The next thing we have to do here is solve for y. We have to multiply this out. So it's going to be xy plus x is equal to 2y minus 3. Okay. Now, in order to solve for y, we got to get all the y's on one side here, right? So let's go ahead and say this is x plus 3. We're going to add 3 to both sides. And we're going to subtract xy from both sides. So we have x plus 3 is equal to 2 minus x, 2y rather. 2y minus xy. Y is common to both of these now, isn't it? Right? It's in both of these terms. We could factor it out. So we could get x plus 3 is equal to y, 2 minus x. Okay. And now to get y by itself, we're just going to divide by 2 minus x. So we have x plus 3, 2 minus x is equal to y. Okay. Let me show you one more thing. Like say, for example, we were back at this section. Okay, everybody's going to get to this part. It's just what do you do from here that's going to be a little different. Okay, so we're going to have xy plus x is equal to 2y minus 3. What if I change things around? I put the y's on this side. So we'd have xy minus 2y, right, subtract x from both sides, is equal to negative x minus 3. Yeah? And then we'll go ahead and do the same thing. We're going to say this is y, x minus 2 is equal to minus x minus 3. We're going to divide both sides by x minus 2. Okay. You guys don't even have to go look in the back of the book. You just type it in. It tells you whether or not you're right. Oh, you guys haven't made our problems. Man, they would. Okay. You have to look in the back of the book and they'd get something different, and you'd have to figure out, like, what did I go wrong? Did I go wrong? If you're looking in the back of the book, or if you're working with somebody else, this answer and this answer are the same answer, okay? It's just, where did you put the negative sign? The top or the bottom? Did you distribute it through, or did you leave it where it was? Okay, they're all the same. All right, now let me show you what's going on. Let me show you something else that's going on. Let me look at my original problem here. 2x minus 3, x plus 1. What is the domain of this function? Right, it's all the numbers except for -1, right? So it's all the numbers except for -1. In interval notation, that's -infinity up to -1, union -1 up to the rest of the infinities. Okay, what's my range? Normally, I don't like to ask about ranges, but we know what the horizontal asymptote is. We know it doesn't cross, so it's 2/1. So this function is all the numbers, right? The range is all the numbers except for 2. So it's -infinity up to 2, union, and then 2 off to positive infinity. Okay, so domain, all the numbers except for 1. Range, all the numbers except for -1, rather. All the numbers except for 2. How about here? Okay, how about here? Well, if we look at this, right, degrees are the same, and my horizontal asymptote here is -1, right? We have a horizontal asymptote at the line y equals -1. Right, the line y equals -1. We have a vertical asymptote at the line x equals 2. So the domain in the inverse function, right, the domain over here is all the numbers except for, domain, all the numbers except for 2. Right, all the numbers except for 2. And the domain, or sorry, the range rather, is all the numbers except for -1. You ever see any of that? You ever see something like that before in relation to this problem? You know, here's the domain of the original function. Here's the range. Here's the range of the original function. Every the numbers except for 2. Here's the domain. That's how that works. Okay, so the domain in the first function, that's the range of the inverse. The range of the first function, that's the domain of the inverse. Okay, it always works that way. That's fine. All right. So that's what we're gonna. I'm not gonna type this one in because I've botched it, but that's how you do that. Okay, that's how you. That's one of the ways you can check. I love the fraction one. Okay, quite honestly, you should practice the ones with the fractions in them, because solving this mess down here, that's a very important skill you're going to have when we get to logarithms. Okay, let's go down here. Excuse me, this one, yeah, let's see what the next one looks like. All right. Parts 1 to 8, good grief, what are they going to ask? Seems like it's going to be a long thing. All right, let's go ahead and graph this thing. Do we have instructions for how many points we need? I don't know. But, oh, we do have x less than or equal to 0. So we're not going to graph anything over here, right? Because we're on my axis over here. So I know what a graph of x squared minus 2 looks like, right? I know, right, here's x squared. And we also know that, you know, this was a vertical shift down 2. Again, I'm not going to be quizzing you on vertical shifts or horizontal shifts, but I do want to take the chance to reinforce it, because you did learn it last year, and it is a really nice and easy way of kind of getting through the rest of your college rest of your calculus classes to know what these look like. All right, it does help. So, yeah, no, thank you. All right, so this one is just, we cut off the right-hand side, right? It's just the left, so it's just going to be this. All right. So we need a couple of points, I think, right? We need where's the intercept? If x is 0, then y is -2. And then without looking too much into it, right? We could say x squared minus 2 is equal to 0 to get the intercept. So we have x squared is equal to 2, x equals plus or minus square root of 2. And since we're on the left-hand side, we're going to want the minus part. Okay. So here I'm going to want, did you really not give me a good tool for this? You did not. Oh. All right, let's not do it that way. Let's pick your favorite number that's smaller than 0. How about -1? All right. So let's pick your point. -1, what was it, -1? All right. And then we'll go ahead and put our vertex. And then we'll, choosing how the curve opens, and then we will plot another point. Okay. And that's our, oops. Oh, we have to erase this. Oh, I'll bet I know. Let's try the scissors. Oh, I don't think that was it. No, that definitely wasn't it. And we were going to hit there. And then we're going to snip. Plot a point to edge to the, you would like to cut the graph. I would like to cut the graph at 0, -2. There. Okay. So the process for doing that, this was involved. Okay, so it might take you 1 or 2 to get the right answer with this, but we took the scissors and we found the point in the middle that we wanted to get rid of. And then when we were done with the scissors, we took the eraser and we said, get rid of that. All right. So we're going to recheck that, and now we're going to be happier. Okay. So that's not always the easiest thing to deal with. Okay. Is it a one-to-one function? Well, it is now. Right. We cut half of it off and down one-to-one function. So yes, it's a one-to-one function. You're going to make me check every time, aren't you? Okay. What's the domain? Well, domain is, right, -infinity up to 0. All right. So these are the x values. Oh, this is not right. You can actually be 0. It's fine. So I need this one because we need -infinity, and 0 is that point that's included. All right, it's happy. What's the range? I need one of those. That's -2, right? Up to all of it. Right, an equation for f inverse. Okay, now we're getting there. So what do we have here? We have x squared minus 2. All right, write the problem down with the y's. Swap the variables. So we have x is equal to y squared minus 2. Solve for y. So we have x plus 2 is equal to y squared. And y is equal to plus or minus x plus 2. This is the one we want. Right? That's the one we want. So the x's are positive, but the y's are going to be negative. Okay, the y's are going to be in third quadrant. Oops. I wanted to go back over here. Okay. So f inverse, see it now? So we have negative. we have, what is this, x plus 2? Okay. Also, notice our vertical shifts went to a horizontal shift, right? It's kind of neat. It's happy. And now the last thing we get to do is graph them both on the same coordinate system. Oh, I'm sorry. What do we have here? We have x plus 2. So if x is negative 2, right, then we end up with 0. All right. Oh, no, end up with 0. What am I doing? All right. And now we're going to come up with something over here. How about we pick, hey, 6 minus 2, right? 6 minus 2 is 4. Take the square root, 2. Okay. So I put 6 in here, it's plus 2. 2 plus 2 is 4. And take the square root. Okay. So we're picking a number here we can take an easy square root of. So I'm going to pick 2. 2 and 2 make 4. Good. And we're going to go ahead and plot the point. Oops, I don't want it there. What did I do wrong? I don't like the way that looks. It's not symmetric. It should be symmetric. Oh, it's negative. That's it. It's negative. We're not here. We're down here. All right, that's better. Okay. So I forgot my little sign over here. Now that I remembered, it looks good. So one thing I do want you to kind of pay attention to is if we drew a line y equals x through this, right? If we drew a line y equals x, right on the diagonal here, these two functions kind of mirror image the y equals x line, and that's what you should be seeing. Okay, that is exactly what you should be saying. All right, pretty happy with that. Write the domain and interval notation. So domain of f inverse, right? We have -2 forward. -2 up to infinity. And again, we can go back and look at the range, right? -2 to infinity. Now my domain, -2 to infinity. Ooh, that's not right. So if I say check it, it's going to tell me it's wrong because infinity gets a one of these, right? So let's go with that. Let's say -2, and then we have infinity. Infinity always gets the curved one, always. Okay, what's the range? And again, you could do this, but we could also go back up here and say what was the domain here? Okay, so it's 0 to -infinity. Range is this one. We want 0, and then this guy is going to be -infinity. Yeah. Wait, what did I do? Range of this guy here. No, we are all the legal values of y. 0 is fine. And then we're going to -infinity. What do they not like about my... I wish I could get something more of a hint than that. I don't know what I wrote. Oh, that's why. I think they like that. No? What am I missing? I'm going to say one more time just for the sake of saying it, but right? Y values here, and then we are, what am I not seeing? Hold on. Oh, I think I'm backward. Okay, that's why I'm writing it. I'm writing it backwards. It's not. It's negative infinity up to 0, not this way. There we go. All right, they're happier now. Get the paying infinity dollars in debt is worse than not having any money at all. Okay, gotta remember that. Okay. Oh, because this is just a smaller. Oh, why do they switch? Why do the domain and range switch? Is because we are going we are flipping them across the y equals x line here. Okay, so we're flipping them across. So if you've got a function like this for f, right? It's mirror image, right? I was always my textbook had a lot of things where you had to draw this thing on the opposite side of the line. I'm glad your textbook does not do that because I was never good at it. You can see this. So we're flipping across the y equals x. So what used to be the domain is now y stuff and is now the range in the inverse. And what used to be the range is now back into the domain, the inverse. Okay. So because we're flipping around, flipping y equals x, or x equals y, the domain, the x stuff in your f turns into the range stuff in your f inverse. And the same thing, right? Your range stuff, your y stuff in your f is going to flip and be your domain stuff when you flip. Okay, so when we flip that y equals x, that's why that works that way. Yes, the inverse should be symmetric over the x equals y line, despite how I've drawn it. Yes. So anytime you draw it and you come up with like something like that, you should have a, well, let me do it this way. Yes, if you want to draw that and or just kind of estimate looking at it, you should be able to draw through the y equals x line. So if we have a function that looks something like that, then its inverse is going to look like that. And they are both symmetric. They both dance around this line here. Okay. Sometimes it's harder to see because you might get functions that look something like the one that we just did. Okay. It's harder to see with this one if you did this by hand because it's hard to see whether or not this is symmetric about y equals x. But if you're careful enough in your graphing, or maybe you're using Desmos, you should be able to quickly inspect it to see whether or not you got the right answer because it should be symmetric about that line. All right. So that's good. It's excellent. And if you're better at drawing this than I am, then that's fantastic. That's not a high bar. Okay. It's really not a high bar. So I hope you are. Okay. But yes, they are symmetric about the line. And because we're flipping x's to y's, we're flipping x stuff to y stuff, our domain and our range are going to swap as well. All right. So let's see here. All right. Let's do one more. Can we go further? See, this one asks you specifically about that, right? If we just swap the domain and the range, that's all you have to do. Okay. Okay, so if we know that the domain here, right, we have f, we have the domain, it is 0 off to infinity, and then the range is negative infinity up to 4. Then in f inverse, this is going to come up here. That one's going to come down there. Okay, so my domain here, right, is negative infinity up to 4. And then the range is going to be 0 to infinity. Okay, so that they just flip, and that's great. So the range, we have negative infinity up to 4. All right, and then in the range, this again, we just flipped it. So we want 0 and then to infinity. Right. So that's all you have to do with those. Just remember that the domain and the range is flipped and the inverse. All right. Let's go on. Oh, they do make you do this. Oh no. Well, let's see. Well, this is here's something you can do. Okay. Your inverse, your y's and your x's are going to be swapped. So if I have to plot points, I'm a little bit better because this is the 0.40. The inverse is going to have the 0.04 in it. Okay. And then since we're at the point, right, 1, 2, 3, or 3, -5, we're going to go to -5, 3. All right. And this is the point here. This is -2, -6. So -6, -2. Hopefully I graphed those correctly. First point. Second point. Third point. All right, so that should be the inverse function. All right, so let's see here. Wow. All right, so again, if I've got some points I can kind of plot, then I can go ahead and figure that one out. But one of the things about being inverse around the side is this function is already kind of inversed around the side anyway, right? It looks like, what's this? This is 2. Looks like this one. Yeah, it looks like that one. Because this one had a, looks like an asymptote at 2. So the range isn't going to hit 2. So the domain here should hit the same one. All right. So a couple, let me just do 2 more things on this one and we'll adjourn. All right. So what if we have the function 1 over x? All right. So we have y is equal to 1 over x. And then what's the rule? We swap, right? So we swap. Let me see, this is x is equal to 1 over y. And then the next step is to solve for y. So we have xy is equal to 1, and then y is equal to 1 over x. Wait a minute. Is it possible for a function to have its own inverse? Right? Is this possible? Oh. Is it possible? Oh, let me not write it that way. Is it possible for f inverse to be itself? Yes. It's right here. Okay. There's several functions that do this. Okay. There's several functions. You can work them out to see, can you do this? So yeah, that actually happens. One of my favorite ones for this, back in the early days of the internet, okay, when email was first a thing, if you didn't want somebody reading over your shoulder and seeing your email, because we always had to do it in a computer lab, you could there's a command called rotate 13, rotate 13, route 13, and it would move all the letters up by 13 positions. Okay, which means, you know, we're not talking about a serious like cipher here. Okay, we're not really writing in code. This is called the Julius Caesar code, I think, because that's what they would do, is they would just shift the letters. Okay, in Bronze Age, this was, you know, cutting edge technology for encryption. Information age, not so much, but it does keep somebody from reading your messages with they're standing next to you. So if you had something personal you didn't want somebody else to read, you would hit RT13 and it would shift all the letters away. The best thing is that you didn't have to write something to decode this thing. All you had to do is shift the letters again forward 13 and you unencrypted your message. So this thing, both this command, shift your letters 13, both encrypted and unencrypted your message. So this is an example, not a cheesy math one, of a function that is its own inverse, right? You could encrypt and unencrypt in the same set of code. You didn't have to have a untangle this. Okay, just do it again. So be careful of functions that are their own inverses. Okay, I always tend to like those. So that's something that's possible. And then, shoot, what was the other one I was going to tell you about? Damn it, I think I lost it. It's lost the time. Okay, we won't worry about it. I can't think of it. Okay, it wasn't hugely important, so it's okay. All right, so there we have with inverse functions. Just to give you a heads up about what's coming next, we do inverse functions because the next thing we do is exponentials. And then after that, it's everybody's favorite with logarithms. Okay. And I'm going to go off on the assumption that having finished college algebra, you were probably not so happy with the logarithms. I'm just going to guess that you haven't done a lot of these because I know how college algebra programs tend to go. Exponentials, we'll talk about it, but I'll talk fast. So I'm gonna, is it safe to assume that, is E a number to you? And I'm gonna kind of go with the assumption that you know that E is a number, but we'll still go over how to get it and what it means and what we're gonna do with it. Okay, but I'll go a little bit faster over the exponential part, and I'll try to go again real super slow over the logarithm part because like I said, I know that your experience with this is probably not so much. Okay. I do too. The last section was a pain. This one is much nicer. So, all right. So we'll call it there. We'll stop. I'll stop